On the journey of humanity's understanding of the universe, there is a peculiar entity that refuses to comply with the grand unified theory, and that is gravity. If gravity didn't exist, quantum theory could explain the universe, but, of course, there would be no quantum physicists in the universe either. You must know what gravity is. It controls the motion of stars, creates black holes, and makes apples fall and hit you on the head. These, indeed, are the deeds of gravity. But, if you think carefully, do you really understand gravity? Although gravity is widespread in the universe, when compared to the other fundamental forces, strong nuclear force, weak nuclear force, and electromagnetism, you immediately notice that gravity is quite unique. The most crucial difference is that gravity is incredibly weak compared to the other forces, and it can only cause attraction between objects, not repulsion. This peculiarity makes gravity stand out. Moreover, when viewed from the perspective of quantum mechanics, gravity becomes even more bizarre. So, why do scientists find gravity so vexing? It's because understanding the workings of everything in the world hinges on mastering their operational patterns. When we can probe the underlying operational patterns of the universe, we can use these patterns to predict the future. Physicists always aim to understand the universe and the matter within it through patterns, which is why they are fervently seeking a grand unified theory. However, the nonconformity of gravity is a significant obstacle to achieving this ambition. In this issue, let's delve into this strange force of gravity. From the most intuitive perspective, the reason we can stand on Earth without being thrown into space is gravity. Without gravity, the entire universe would become a dark and chaotic mass of dust and gas, devoid of stars, planets, and life. Gravity's presence is widespread, but its force is remarkably weak. Just how weak is it? Relative to the other three fundamental forces, gravity's strength is about 10 to the power of 36 times weaker. This number is so large that it becomes incomprehensible to us. You can roughly grasp this by imagining that the number of all atoms in the entire universe is around 10 to the power of 80, so gravity is weaker than the other forces by a factor of 10 to the power of 36. To gain an intuitive understanding of how weak gravity is, you can try this small experiment. Pick up a magnet and attract a metal nail above it. At this moment, the tiny magnet is counteracting the gravitational force of the entire Earth on the metal nail. Seeing a small magnet counteracting the entire planet's force demonstrates how much weaker gravity is compared to electromagnetism. So, since gravity is so weak, why is it so crucial in our universe? Why shouldn't we just disregard it? From an intuitive perspective, if something is so much weaker than another thing, it should be completely overwhelmed, right? It's like when a typhoon strikes, who would care if a butterfly is fluttering in the storm? However, the answer is that in the case of extremely large scales and masses, gravity becomes of paramount importance. The strong and weak nuclear forces are short-range forces, typically only effective at subatomic distances. Electromagnetism is a long-range force, but why can it dominate the motion of stars and galaxies? The key lies in gravity's intriguing property. It is a one-way force, causing objects to only attract each other and not repel. The strength of gravity is directly proportional to the mass of objects, and mass cannot be negative. On the contrary, electromagnetism introduces two types of charges, positive and negative. Similarly, the weak and strong nuclear forces have similar attributes. But in our universe, mass cannot have a negative value, which means gravity will not cause particles to repel each other. This is a crucial distinction. It means that the gravitational forces between different particles can never cancel out but will always stack up. On a large scale, electromagnetic forces can cancel each other out. For instance, if the Sun carried only a positive charge and everything on Earth only had a negative charge, the electromagnetic force between them would be significant and far exceed gravity. However, statistically speaking, there are roughly equal numbers of positive and negative charges on Earth. The Sun is likely similar. So, between the Sun and the Earth, there are both attractive and repulsive electromagnetic forces, which seem to cancel each other out. But this is not a coincidence. Due to the strong electromagnetic forces at work, charges are continuously readjusted until all remaining imbalances vanish. This process was likely completed around 400,000 years after the birth of the universe. Almost all macroscopic matter exists in a neutral state, and electromagnetic forces are balanced within planets. It's challenging to find a naturally formed macroscopic object in the universe that is entirely positively or negatively charged. So, with the overall electromagnetic forces between the Earth and the Sun being nearly zero, and the strong and weak nuclear forces being short-range, gravity emerges as the dominant force at the scale of planets and stars, as all other forces reach an equilibrium. Gravity depends on two parameters: the mass of two objects and the distance between them. Since mass cannot be negative, the gravitational force between two objects continuously increases with the number of massive particles they have. To summarize, gravity has two distinct characteristics, and we still haven't fully understood why. The first characteristic is that it's incredibly weak compared to the other fundamental forces. It's like others are driving tanks, while gravity is riding a tiny pony. The second characteristic is that other forces are bidirectional. They can attract or repel each other based on the properties of the objects involved. However, gravity always exhibits mutual attraction. This obvious inconsistency means that it doesn't fit into our existing understanding of the universe or follow any important internal logic that we've discovered. Indeed, that's the case. At a deeper level, gravity becomes even more peculiar. Currently, our best mathematical framework to explain all matter, particles, and the three fundamental forces is quantum mechanics. In quantum mechanics, everything, whether it's an object or the forces between them, can be described as particles, which can be divided into tiny units called quanta. When one electron pushes another electron, it doesn't use some invisible or mysterious force or telepathic connection to drive it. Physicists believe that this interaction arises from one electron exchanging a particle with the other. This particle transfer can transfer some momentum, similar to two electrons passing a basketball to each other. In the case of electromagnetic interactions, the exchanged particles are called photons. In weak interactions, particles exchange W and Z bosons, and in strong interactions, they exchange gluons. This standard model of particle physics successfully explains a wide range of natural phenomena observed in the laboratory. It can even predict things we have yet to discover, like unknown particles or the Higgs boson. However, it faces a significant issue: it cannot provide a satisfactory explanation for gravity. You might think that by now, science has explained everything, but ironically, gravity, the most common force we encounter, remains unexplained by current quantum mechanics. There are two reasons why it can't be explained. The first reason is that if gravity were to be integrated into the standard model, we would need a particle to transmit gravity. Physicists have named this hypothetical particle the graviton. If such a particle existed, it would mean that when you are attracted by gravity, every particle in your body and every particle on Earth would be continuously exchanging something with each other. However, the problem is that nobody has ever observed the existence of gravitons. So, this theory could be entirely wrong. This is the first reason. The second reason is that we already have a theory that explains gravity very well. This theory is Einstein's general theory of relativity, proposed in 1915, and it is already quite perfect. General relativity interprets gravity from an entirely new perspective. It suggests that gravity is not an interaction between two objects but the result of the curvature of spacetime itself. According to Einstein, if we imagine space as a kind of flexible fluid instead of an abstract, empty concept, then gravity becomes straightforward because the presence of mass or energy bends the space around it, thus altering the motion of objects. In this theory, gravity is not a force but rather a representation of the curvature of spacetime. There is a simple phrase to describe Einstein's general relativity: matter tells space how to curve, and space tells matter how to move. In this description, there is no force between matter and space. General relativity posits that the reason why the Earth orbits the Sun and doesn't fly off into space is not because some force traps it in the Sun's orbit. Instead, it orbits the Sun because the space around the Sun is bent in a particular way. In this curved space, the Earth moves as if it were following a straight path, but it actually traces an elliptical trajectory. A common analogy is to envision space as an elastic rubber sheet. When you place the sun on the sheet, it causes the entire sheet to depress downwards. If you then bounce a small ball on the sheet, the ball's natural straight path becomes curved when it approaches the sun's region due to the bending of the rubber sheet, which is like curved spacetime. But in this process, there is no force pulling the little ball to make it orbit around the sun. Of course, this is just an intuitive analogy, and the real situation is described using mathematics. In this way, gravitational mass is no longer seen as some special charge of certain particles, similar to electric charge, measuring how much an object can bend the space around it. Although this statement may sound strange, it successfully explains local gravity, cosmic scale gravity, and many wondrous phenomena in space. We will talk more about space and its curvature in later episodes. Relativity is a very great theory. It predicts the existence of black holes, explains celestial motion, and even provides us with GPS positioning. However, there is one problem. General relativity is perfect. Quantum mechanics is also perfect, but we have not been able to merge the two theories together. The difficulty in unifying these two theories lies partly in their fundamentally different perspectives on understanding the world. Quantum mechanics regards space as a flat background, meaning space does not bend. On the other hand, general relativity sees space as dynamic and elastic. It is a thing. Going deeper, relativity views gravity as a phenomenon, a manifestation of the bending of space-time. In contrast, quantum theory sees any force as being caused by little balls flying around in space. So, if everything in our universe, except gravity, follows the laws of quantum mechanics, then gravity should also follow the same rules. Unfortunately, until now, there has been no evidence to prove the existence of gravitons. Moreover, we cannot even imagine what quantum theory would look like once it is unified with general relativity. Quantum physicists typically predict the existence of certain particles first and then confirm their existence through experiments. For example, both the top quark and the Higgs boson were discovered in this way. However, when physicists attempt to unify these two theories from a mathematical perspective, they have never succeeded. Instead, they end up with many absurd conclusions, such as infinite quantities. Currently, string theory holds the most promising hope for unifying relativity and quantum physics, but progress in this field has been very slow, and it remains in the realm of theoretical speculation without concrete evidence. In conclusion, gravity still holds many mysteries. Nevertheless, scientists will not let these mysteries linger forever. They must take action. Currently, one method is to test the laws governing the universe through experiments and devise clever theories to explain the phenomena we observe. Ideally, we hope for an observation that can test both general relativity and quantum mechanical effects. If one of them is correct, we hope to distinguish it in this experiment. For instance, if we observe two massive objects exchanging gravitons, it would confirm that gravity is indeed a quantum phenomenon. Are there places in the universe that could meet both the descriptions of general relativity for supermassive objects and the descriptions of quantum mechanics for super-small spaces? Indeed, there are such places, the interior of black holes and the starting point of the Big Bang. However, studying these two scenarios is very challenging. Black holes can be entered, but once inside, there is no way out. As for the starting point of the Big Bang, it is incredibly distant from us. You may have often heard that scientists have studied up to 10 to the negative power of how many seconds after the Big Bang began. Why do they push the limits and try to approach the starting point of the Big Bang? Because through its study, we hope to attempt unifying quantum physics and relativity. Another possibility for observation is the collision of black holes, where two supermassive black holes collide with each other. This could offer a way to probe gravity on the quantum level. Of course, this doesn't mean that we manipulate two black holes to collide. Currently, humanity does not have that capability. It's just that the universe is incredibly vast, and we can find various events happening in many directions and distances. With patience and diligent searching, we can find almost anything we desire, such as colliding black holes. When two black holes approach each other, they want to devour each other, and they will start rotating faster and faster, entering a death spiral. In this merging process, gravitons may be emitted in all directions, and our task is to observe these gravitons. However, it is not easy. Gravity is incredibly weak, so even if a graviton flies past you, you would hardly notice it. Remember neutrinos? They can pass through a light year of lead. But compared to gravitons, neutrino interactions are much stronger. By calculations, even near a strong source like a black hole, we would need a receiver the size of Jupiter to detect one graviton every 10 years, assuming gravitons really exist. After discussing the method of detecting black hole collisions, let's talk about another approach: finding or designing an experiment that gives different predictions from the two theories. We can test which theory is correct and which is not through such contradictions. For example, exploring the inside of a black hole, general relativity tells us that there is a point called a singularity within a black hole. At that point, the mass density is extremely high, and the gravitational field's intensity tends to infinity, while space-time will curve into unimaginable forms. General relativity suggests that such a singularity can exist. However, quantum theory disagrees. According to the basic principles of quantum theory, an object cannot be reduced to a single isolated point. When space becomes extremely small, its uncertainty becomes extremely large. So, in this situation, one of the two theories must be wrong. If we could know what the inside of a black hole looks like, we would gain a crucial clue to understand how quantum mechanics and gravity interact. However, the realization of this idea is incredibly daunting. Besides the question of whether we could survive the journey, the process of entering a black hole might already tear us apart. Are there any other possibilities? One exciting topic in recent years is gravitational waves. When two massive black holes accelerate toward each other and merge, they create a ripple in the surrounding spacetime, much like the way two boats in water rotate around each other. This ripple is known as a gravitational wave. In simple terms, moving masses disturb space, and this disturbance propagates like ripples. When a gravitational wave passes through, every object along its path will be stretched and squeezed. A circle may instantly become an ellipse, and a square may become a rectangle. However, such deformations are nearly impossible to observe. The spacetime distortion caused by a gravitational wave is about 10 to the power of 20 times smaller than the original size of an object. To put it in perspective, if you have a 10 light-year long stick in your hand, how much would a gravitational wave shorten it? By 1 millimeter, an effect that is extremely difficult to measure. This is where human ingenuity comes into play. Scientists built an experiment called LIGO, Laser Interferometer Gravitational Wave Observatory. It consists of two perpendicular 4 kilometers long pipes. Scientists use lasers to measure the distance changes between the top ends of the two pipes. When a gravitational wave passes through, it stretches space in one direction and compresses it in the other. While we cannot directly measure the pipe length changes with laser back and forth, we can measure the interference patterns produced by many reflections of the laser within each pipe and accurately deduce whether space is being stretched or compressed. The LIGO project, with a cost of $620 million and decades of observation, finally identified the first signal of a gravitational wave in 2016. This discovery provided perfect confirmation of Einstein's theory that gravity bends spacetime. Unfortunately, we cannot deduce from gravitational waves how gravity operates at a quantum level because gravitational waves are not the same as gravitons. It's like proving the existence of dinosaurs but not finding a particle called dinosaur. Regardless, the discovery of gravitational waves is a significant advancement in human science. After all this discussion, the ultimate conclusion is that gravity is still very special. Why it is so special, we still don't know. Perhaps gravity is inherently unique, and our scientists hope to find a grand unified theory where all forces follow a fundamental principle. We are still not clear about the principles governing most of the universe. Many times, our assumptions are overturned, or certain theories only apply to specific situations. Maybe gravity is just like everything else we've seen before. It's fundamentally different. Perhaps it's not special, and the universe is just designed this way. Our goal is to understand this universe. Perhaps we should avoid preconceived notions about what it should look like. Currently, there is a hypothesis that uses extra dimensions to explain why gravity is so weak. Gravity's strength is weak because it is diluted into other dimensional spaces, forming tiny loops that we cannot see. If we consider other dimensions, the strength of gravity would become as strong as the strong nuclear force, weak nuclear force, and electromagnetic force. In short, unveiling the mysterious veil of gravity is crucial for understanding the universe we inhabit. Gravity is the only force that plays a role on a macroscopic scale, meaning it is the key force that determines the shape and ultimate destiny of the universe. Through the study of gravity, we have also discovered dark matter and dark energy. The fact that gravity can bend space-time leads to many exciting possibilities. Due to the speed of light limitation, we might never be able to visit star systems outside the solar system because their distances and our travel speed would not allow us to reach those faraway places within our lifetimes. However, if we could unravel the mystery of gravity or learn to bend space-time actively, such as creating a wormhole, we might truly explore the entire Milky Way galaxy.